All right, afternoon, everybody. Thanks for joining in. We have a two-part talk this time, with the second part going to be occurring a little bit later in June. After talking with Jeronimo, he said that this would make the most sense to sort of go over the theory first and then the practice a little bit later, and I think that was a perfect idea. So Jeronimo and Italo and the entire team from AMPATH and FIU are here, and they're going to go into the details of talking a little bit about how they're doing some research on handling microbursts. So Jeronimo, I'll turn it over to you.
Thank you, Jason. Good afternoon, everyone. Welcome to join the session. Yes, like Jason was talking about, we decided to break it down, this presentation. This whole work is a consequence of a paper. And we decided to break it down because we understand there is a new generation of network engineers joining the In-band. And I think it would be good to have a little bit more context for this new generation, and also to refresh the knowledge, go back a little bit back to the books and protocols before we start getting more complicated, more complex solution. So this whole two-session part is to talk about how we're handling microbursts here at AMLite. The first part is to talk about the challenge of detecting. So we go a little bit of explaining what is a burst, what is a microburst, what is so challenging to detect those. A quick step back to talk a little bit about the protocols and the fundamentals of how the devices handle packets. And then we jump into the AMLite INT collector auto solution that we call adaptive approach. Then the part two, it's why and when is detecting microbursts important. So this is where we're going to be presenting use cases. We're going to be showing some science drivers that we model and showing how those science drivers are affected depending on the scale of this microburst. So then it will help the audience to understand, is this a problem that I have? Is this something that I should be concerned or not? Because detecting those are not simple. In multiple cases, will require some investment to build infrastructure to do this. So that's the reason we decided to break it down. So today will be almost the hour. You feel free to interrupt me at any point. If you have a use case that you want to also share, that would be great. But I think in terms of use case, then it would make more sense for the second part in June 2nd. But if you have questions, let me know. So I wanted to start the presentation with this paper that we found about Facebook. Facebook did a data center incident. It's a data center, it's not an NRAM, but it's all the network incidents that they had from 2011 to 2018. And you can see here in the pizza chart that there is a massive section, like 29% of those incidents, they did not find the root cause, right? So for every problem, they try to understand what is the root cause of those. And for 29%, they report that was called undetermined. And when they try to explain why they were not successful, they said that because those were transient events, or they're too small, or they didn't have the tools or the technology to correlate events to determine what was the problem. And this is examples of transient events here are bursts or microbursts. And that's the reason we decided to talk a little bit about microbursts, but not to say that, oh, it's just academic networks that have this, not just data centers. All of us are impacted by microbursts. In fact, it was one of the reasons INT was invented, because of the stock market. So let's dive a little bit into the description. So starting with the first one, the most basic one, network bust, for those who don't know, is a condition in which network activity rises suddenly for a short period of time. A burst is a transient elevation in network activity. So the reference is down here at the bottom of this slide. And it's very common for research and education networks. We tend to have bursty networks because of the nature of what we do. We do a lot of data transfers that are not planned, are not constant. So we have those bursty network infrastructures. And then what we do to accommodate those is over provisioning. It's been something that's part of our blood by now. And it's a good way to handle those bursts. But there is a few things like a duration and a scale of a burst that those two, they don't have like formal definitions, right? So I think it's based on one's experience. So some people say milliseconds, some people say seconds, some people say above the committed information rate. Some people say that if you use more than 50% of the interface bandwidth, that's a burst. If some people say that it's 4 or 5 times the growth over the previous number of seconds. So it's hard to define exactly what's a burst. It's easier to see than to explain than to code, but I think that should be enough. So why should we monitor those bursts? Well, they can quickly deplete the bandwidth. They can fill out the queues and the buffers, and because of that, they get introduced to delay, jitter, and packet drops, right? So, and you can find those if you have graphs for interface utilization. You can see those bursts sometimes for queue or even for flow. There are multiple ways to see those bursts. A key thing is that to be able to see this, you have to keep querying the network, right? You have to collect the counters and you have to plot the bandwidth utilization. And as network operators, we usually do this from 15 to 300 seconds intervals. In the past used to be the 5 minutes, but now the technology enables us to go a lot closer to the second or even sub-second. I would say 150, 100 seconds is pretty good for this. But the number to keep in mind is the lower the number, more granular the measurement. So it makes it easy to see the burst and to understand when it started and what was the size of it. But again, the lower the number, higher will be the CPU CPU utilization, disk space consumption. So you have to always find the balance of those. And this is an example. This was 2 days ago. Here I'm like, this is production traffic. It's just to show those bursts, right? So those peaks of blue and the orange lines represent bursts. So you have very short ones here, multiple seconds. But you see that most of the time the network is pretty quiet. This interface at least is very quiet, 3 to 4 gigabits per second. But suddenly there is a burst of 60 gigabits per second, sometimes 10. There's personas that data transfer. There's LHC1 traffic. So it varies a lot. And this is the importance of having this kind of monitoring is for you to actually see those bursts to try to understand their impact. And then there is the microburst, right? So what makes a burst micro, right? So network microbursts are sporadic bursts of traffic, but they occur in a very short time scales. And this is another definition that we don't have. Very short defines per vendor, per author. This with Facebook and their publications, they usually say microseconds time scale. Huawei, Arista, most of the science authors, they talk about milliseconds because it's easy to implement and create a lab millisecond based. So they usually go in by a millisecond. My own is like any time scale that my network monitoring system cannot detect the burst, I would call it microburst. So if you have a device that only supports monitoring every 14 seconds, and then you have bursts that you cannot see because they're shorter than this, I would call that burst a micro because you don't have visibility. But anyway, it's up to you to find your own definition and understand how, what kind of time scale becomes a problem for you. And you can use the same approach to detect those interface utilization, queue utilization, flow utilization. All of those give you pretty nice results if you have the proper tools to see this. But it's important to keep in mind that not all microbursts are necessarily attack, right? Not necessarily bad. IPTV and distributed sensors are applications that are known for sending microbursts. I'm not saying multiple gigabits per second, but it's something that out of nowhere you send a lot of traffic, then you stop, right? So even the video compression makes create those microbursts sometimes. So it's important for you to know what you have in your infrastructure before defining what a microburst is. So why is detecting a microburst complex? There are a few topics that we have to discuss first. So there is the first one I would always say is the control plane at the data plane synchronization timers. Then there's the technology. What is the right kind of technology, right approach of getting data that you have to go with to detect the microbursts? What is the ideal measurement or gathering query interval? So how often do you want to query your devices? How often do you want to receive reports to understand if you are monitoring the microbursts properly or not? And also, there's the disk space consumption, right? So most of the time, if you do the monitoring, you want to save that information. So if you retrieve data from the router, you don't want to just look at the lead, you want to store that. So depending on the size of what kind of microburst you're pursuing and how many interfaces you have and the number of services you have, that's a substantial amount of disk space that I'm going to present some examples later. Then now going back a little bit of background to help us understand how we can start answering those questions. So the first one is how packets are counted by network devices and how fast can we have access to those, right? So to explain those, I'm gonna go a little bit more generic. So this is a picture of a network device in green. You can pretend that this is a switch or this is a router. And inside that device, you have multiple planes. The main ones are the control plane, the management plane, and the data plane, right? So the control plane and the management plane are those on top. They share the same generic CPU. So it's just like sometimes are the same Intel CPU. They are for any purpose, general purpose. And the control plane has the responsibility of creating and maintaining the routing and switching tables, right? So OSPF, BGP, LDP, OpenFlow, spanning tree, RSVP, all of those are control plane protocols. And they work as processes in most of the operational systems. The management plane also has multiple processes that talk and export the data in SNMP format, SSH, SFlow, syslog, Juniper telemetry interface, OpenFlow, NetFlow. All of those are also processes that are running in this general use CPU. Each one of those have their own tables and counters. And then we have the one at the bottom that is not a CPU, but is a specialized CPU. That's part of the data plane. And the idea of the data plane is just to forward packets at line rate. So you probably heard like ASICs or FPGAs, NREs, FPC, Tofino, Jericho, FIB, and protocols such as In-band Network Telemetry. All of those operated as very high-speed disks because they want to forward the traffic as fast as possible, right? So they want to do multiple 100 gigs, 400 gigs. That's the ship that has to do the forwarding. Those, they don't care if you do P4, if you do OpenFlow, if you do BGP or MPLS, because at the end, those are just control plane protocols. In the end, everything is transformed in memory access that is pushed to this hardware. And the hardware only does packet forwarding. It doesn't care where the information came from. It has tables and it has actions. So then the CPU has, in those processes, they offer APIs or interfaces for external communication. Those are the blue arrows on top. That's how you connect to that box. That's how an OSPF router talks to another OSPF router. And then you have on the bottom, the orange arrows, which are channels that are used between those planes for communication. That's how the management plane gets the counters. That's how OSPF sends or the routing plane sends a route to the data plane. So there's these internal channels. Those who operate Juniper routers, they know this because we're exposed to this more like frequently, the interfaces, but all the devices have this. And also we have, as part of the inter-data plane communication, you have those timers, right? So that's a kind of it's actually a timer that controls how fast or how often you're gonna get data from one environment to another to avoid consuming extra resources or generating interruptions that could lead to poor performance. So these timers are the ones that we're gonna be talking next. But before, again, just as exemplifying this, Let's pretend that we have this network. They have 2 nodes, 2 switches, and there is a packet represented by the envelope, the blue envelope on top that wants to go from the left to the right. Then once the layer 2 device does the forwarding, this table here goes to the FPGA counters or the ASIC counters, right? So it counts the number of packets, in this case 1, and the number of octets, which is the number of bytes of that packet. That in this case, I'm just using IP, but ignore Ethernet and VLAN, but let's say just IP 1200 bytes. And then after some time, it's not real time. After some time, this data is retrieved by the CPU, and this table is synchronized with the table that is in the CPU and made available to the public, right? Made available to the operators and to the protocols. One important detail here is that those tables, they just count packets. They don't calculate bandwidth, for example. They don't calculate packets per second. They just do counters. They just increment those counters. So then once you have a second packet, let's say 9,000 bytes, then you see that in this table is incremented by 1 and is incremented by 9,000. Again, it does not calculate bandwidth. So every time that you retrieve data from those devices, those are counters that increment. They don't calculate anything that is stateful, right? Because, well, for many reasons, this is not that easy to be done. And those dedicated CPUs, dedicated hardware, the ASIC, sometimes they don't even offer like division operations. So those synchronization timers, how fast they indicate how fast you can access that data. Because if there is a timer to synchronize the table from the general CPU to the specialized CPU, that means that if you query in an interval that is like faster than this, you're gonna get the same data, right? So if the synchronization timer is 14 seconds and you make 2 requests every 10 seconds, in those 2 requests, you're gonna get the same data because there was not enough time for the CPU table to be updated with the specialized ASIC table. So that's the part that it's important to keep in mind. You can only go as fast as the synchronization timer of your device. In some cases, that's configurable. HP enables you to go from 1 to 20 seconds to preserve the device or be more specialized or more accurate. And Dell, the Z9100 switch, which was very common switch a couple of years ago, in the NRAM, only enables like there's no configurations, only 14 seconds, so you cannot go faster than this. And we never tested sub-second, just a disclaimer, but we've seen devices going from 1 to 30 seconds for a kind of older devices or smaller devices. And this table here represents a publication that we made in 2016. That was for OpenFlow, but we did similar work for SNMP and the results in NetFlow, and the results were pretty similar. This here shows how long it takes for the idea is to be on the yellow line is on 100%, how long it takes to get all that data, all the counters updated into the main CPU. So you see that sometimes goes like 8, 9, 10 seconds to get that data. Some devices used to take like 30 seconds. So why is this important? Because if you're doing traffic engineering, that you want to do like any operation, like every 5 seconds, like you want to do load balance using the last 5 seconds of counters, and your device only update the counters every 14, you're not going to get 5 seconds. You're going to get probably 14 or 15. So this that's the part that is important to keep in mind, those timers, because you're not going to get any gain by going faster. You're just going to get pain. Okay, so now that data is available on the main CPU. How can we retrieve those? How can we have access to them? There's 2 approaches. You can go passive, or where the operator has to request those counters. So that's when you send an SNMP get to a device asking for the number of packets of one interface, and then you get a number back, right? So you have to, it's a passive operation. You define as an operator the gathering interval or how fast you want to go. you define what kind of information, you know what the data model is. So if you're asking for a number, you know that you're going to get a number back. So this is the passive approach. And then you have the active or streaming now approach, where you configure the device to, every time there's a trigger or an event of interest, send you the counters. So you get a packet with a report that includes everything that you asked for. There's a complicated data model where you have a lot of information, a lot of counters, and your system has to be prepared to receive that. So this trigger could be timer. For example, you can say every second send me a report, or it could be every time that there is a drop, like, or every time that the queue reach 80%, you can set multiple triggers, and then you decide if the device supports what's going to happen, what kind of report you want to receive after this. And this is the ideal approach for microburst detection, because in the passive approach, you have to keep asking every second, for example, and it's very traumatic for everyone involved. But if the device sends you right away without having to answer to a request, have to pull, create sockets and all of that, it can generate this, sometimes can even generate those reports directly from the data plane. So that makes it super fast, super efficient, and almost no impact to the device. So SNMP is a very well-known protocol. Everyone uses for incoming and outgoing interface utilization. Its space is an IETF standard. It has multiple object identifiers, multiple management information bases, database. So this is the most common, but it's fully passive. I know some people say, oh, but there's SNMP trap. It was a different game. It was a different purpose. It could be used, yes, that's true, but almost no one uses that anymore. SFlow is a streaming solution. It's a sampling approach. So the trigger is every time there's 4,096 packets, I send you a report. And this amount of packets, this sampling rate is customizable. You can do every 1,000, every 100, every 8,000, depending on how much traffic you have and how much CPU you have. So this is a good approach for you to start trying to detect bursts and microbursts, because a microburst is implying a lot of packets in this a very short interval. And if you have sampling that captures this, then at least you know that you had a burst or a microburst. So this is good. The problem with this is it's going to bring a lot more data that you want for a microburst detection. If you're just collecting statistics, that's good. But those reports are created by the device's CPU, the general use CPU. So if you have a sampling approach that is too small, you're forcing that CPU to keep always creating packets. And if you have 40 gig of traffic that generates like 4 million packets per second, then your sampling rate is going to be like almost 100,000 packets per second. So there's going to be a huge impact for that CPU, and you don't want that, because that CPU is also used for BGP, for OSPF, and that's when you start seeing the OSPF neighborhoods flapping or BGP sessions going down, is because someone is using the whole CPU. There's this new solution, like from 3 or 4 years ago, called Juniper Telemetry Interface. Needless to say, it's not a standard, but it's a very good job that Juniper did they create these multiple sensors, they group those sensors, and they export those reports in 1 or 2 seconds to the JTI collector. And those reports have utilization, key utilization, power levels for the transceivers. It has a lot of information, everything being streamed to your collector. So you don't have to know the whole MIB, for example, and all the counters of interest. You just get everything that the router can provide. So it makes it a lot easier. It's very granular. The only setback is that the faster JTI can go is 1 second. And that's not for the PFE, that's not for the interface counters. The interface counters is only 2 seconds. So it's not going to give you millisecond precision or sub-second precision, but it's going to give you very good precision for at least monitor the queue utilization. There's another proprietary solution that comes from Cisco, Cisco telemetry interface. I don't remember the name now. I never used. I know that it's in a PowerPoint, works very well. Those solutions here we have at AMLite, so it's easy to talk about them. But Cisco also seems to have a very good solution, and they have one family called Nexus 9300 that even supports microburst detection directly in the chip. So that solution is very good, but it's very specific family, and there's multiple licenses, but you can get microburst detection. So it's good if you have an experience and you want to share. Great. I never worked with it. The one that we use is the In-band Network Telemetry, INT, the solution that we presented last year here in the CI Lunch and Learn. We have INT in our network. Basically, INT, the trigger is every packet. So every packet triggers a report. That means that if you have one packet, you get one report. If you have a million packets, you get a million reports. And those reports, they come with the packet header and the metadata, the device metadata. So you get the report immediately, is right away. So then you know exactly when that packet landed on the switch, and then you can start putting together all the metadata and calculate the microbursts or the bursts or whatever you want. It's a standard, it's not an IETF standard, it's a p4.org standard. And it's being like standardized for 5 or 6 years now, 2016, 2017, I think in 2017. And the challenge of this is that the data doesn't come consolidated in a report like in JTI, so you get the raw data. So what we do we create an implementation that receives all those reports, parse them, and create the counters and the node in the computer, in our monitoring computer, and then our monitoring software saves the data every 100 to 500 milliseconds, right? So we don't save every report because sometimes you have 4 million reports per second. We cannot handle this. The CPU cannot handle this. The disk cannot handle this. And sometimes even the NIC cannot process all of this. So what we do is that we aggregate those into 100 milliseconds and then we store those. Here, a quick table comparing those, when to use them, where's the challenge with each one of those. I'm not gonna get into the details. This is just a summarized version. This was presented by our network engineer, Renata, during the 2022 TechX. I think it was not recorded, unfortunately, but the slides are online. We can provide if you want it. So this is a good way of summarizing everything that we have at AMLite. Obviously, there are other technologies like port mirror and fiber taps. They are not a protocol, but more like an implementation. What they do is they create a copy of every packet sent to this port mirror port or fiber tap device. And then from there, you can do like intrusion detection systems. You can do protocol troubleshooting. You can turn those into SNMP counters or S-flow reports, or just play with those. They are interesting. It's very hard to use them when you have 100 gig interfaces and a lot of traffic, but they are useful sometimes. But they're hard to scale for you to have this as a main approach for detecting microbursts. Maybe you can do this for one interface, two interface, but if you have a whole backbone, you're gonna have one B or one fiber per fiber, or one fiber tap per fiber. That's very complicated. So again, parts from the slides Renata presented, this is a demonstration, a demo that she created, where she created this ring topology, where there's a traffic generator that sends the packets to a P4 switch, an edge core. Then there's a 40 gig interface that goes to the Dell Z9100, then goes to the Juniper MX204 and goes back to the edge core, and then goes back to the traffic generator. Every device is porting the same they are having access to the same traffic, but exporting directly with their technology. So Dell provides SNMP counters, the Edge Core provides INT reports, and Juniper provides JTI reports. So again, JTI 2 seconds, Dell 14 seconds, and Edge Core is real time, but we aggregate it every 100 milliseconds. So to show here some examples. So again, the interface is 40 gigs. She created 2 flows, one flow of 20 gigabits per second, and then she added 5 bursts of 30 gigabits per second, meaning that she's trying to get to 50 gigs, but the interface is 40, so there will be congestion, and that's what we want to see. And each burst lasted for 2.5 seconds, right? So, and then you can see here in purple, INT with all those valleys and mountains here going up 5 times. You can see the JTI in green, not that much precision. Sometimes they go halfway, sometimes they go all the way, sometimes halfway, all the way, halfway. But you can see that they have 5 events, right? And then when you go at the SNMP, then yeah, there's no precision. The maximum that we got was 29 gigs. There's just one mounting. There is no idea that there is microbursts happening or bursts happening. So here she continued doing the same thing, but instead of 5 bursts, that was 15 bursts of 30 gigs, but now the duration is 200 milliseconds. So now that's when it started becoming a problem, because 200 milliseconds, it's a lot smaller, shorter than 2 seconds that JTI supports. So then you can clearly see that JTI in green, it just became like a flat monitoring, right? It's just one mounting, no peaks, no oscillation anymore. It's even worse than SNMP. But at least reflect the information faster than SNMP. You can see that INT is still doing a pretty good job. I didn't talk about this, but I know the interface is 40. How is it possible that you go beyond 40? It's not an INT fault, it's a Grafana fault. The way how we aggregated data is only support by every second. So when you zoom in here on this part, you're gonna see the 40 gigs. But when you concentrate like 30 seconds, it has this thing that goes over 40. And now she did a third one that then become a problem even for INT, not the INT protocol, but our implementation, because now she's doing 50 milliseconds when the application that we built is configured to do every 100 seconds. So 100 milliseconds. So then you can see that we see all the peaks, right? I don't know if there's 30 of them, but they don't get close to 40 anymore, right? Because the duration of those is half of the interval that we use. So it's only natural that each burst is only reflected as close to half of its capacity. So that's the reason we see 30 gigs here as the maximum. It showed 32, but the same problem with Grafana, in fact, is 30 gigs. Then you might ask, well, if you know that the burst is going to be 50 milliseconds and your monitoring is 100, why don't you change the configuration of your monitor to be 50, right? This is possible. Yes, it is. It's a configuration. The only thing is disk space. Disk space for us is a concern. To be honest, we don't even use 100 milliseconds in production. We use 500. And here's why. If you look at the MLID numbers, we have 20 switches, approximately 14 interfaces per switch in use, and approximately 20 VLANs per interface. If you multiply those, it's 5,600 monitoring items. So each one of those, you have to monitor for incoming traffic, outgoing traffic, errors, pause, and everything else, right? But just picking one monitoring item, just say one of those octets, packets, and timestamp in nanosecond precision, which is 8 bytes. This leads to 24 bytes. 24 bytes per monitoring item. If you monitor this every 1,000 milliseconds, which is 1 second, at the end of the day, you have 11 gigabytes. of monitoring data for that only item, which could be just traffic leaving the interface, not entering the interface, and there's not pause or anything. But if you start like trying to get more granular about this and get to 25 milliseconds or 50 milliseconds to get that test that she did, that's going to be 227 gigabytes a day for just, again, one object, one type of object for all the items. So you can clearly see that there's a trade-off. You have to be concerned about this. The beauty of the solution that we built with the INT collector and INT is that we can go as granular as we have disk space, right? But the thing is, well, we're not going to be buying disks to hold this data for a long time. Even 11 gigabytes per day, it's a lot, because this is not the only item. This is not the only monitoring. And we want to retain this data as long as, for as long as possible. We have flows from 2012. So it would be natural to have something similar for interface in microbursts. Well, and then to the other thing is that due to this amount of data that we have to store, and the low frequency of microbursts is because they don't happen all the time, right? You don't know when you're gonna have one, but you know it's not gonna be all the time. So if you enable something like this, 50 milliseconds, that means that you are always expecting, every 50 milliseconds, you're expecting this, but you might have just once a day. And then you're gonna have all that data that you have to process and clean and maybe throw it away. So we decided to change the approach. We decided to, instead of doing this in a fixed interval like this, then something a little bit more dynamic. And then only store the data. We're gonna parse everything as we receive the data, and then only store if you realize there is a burst or not. So we're gonna store the events. So this is our version 2.0 that we call our adaptive approach. And this is the schematics of the version 1.0 that I presented last year. I'm not going to go into the details. I just want to show what the change is, right? So we have this utilization counters collector that is developed using eBPF XTP. Used to be in the kernel space before the networking stack. It still is for the 1.0, but for the 2.0, this was offloaded to the Mellanox programmable NIC. So this is the problem, is that this module, although it enables us to change the configuration to lower the interval or increase the interval once configured is still fixed. Right? If you set to 1 second, it's going to be always 1 second. If you want to change, you have to stop and then you change. Then after that point, it's only going to be the one that you change. It's not going to be dynamic. And the data is pushed to InfluxDB. And as I mentioned, the interval that we use is the default one, 500 millisecond. So this is the goal for this version 2.0 is to be dynamic and adjusted at runtime. So it's not dynamic in the sense that it learns by itself, but we want to get to that point. So this was our motivation. I know that I showed that slides that compared with SNMP and JTI, and that by itself was a proof that something had to be improved. But that came a long time after this one. This is the real one, where we tried to generate a 70 gigabits per second microburst for only 40 milliseconds with a background noisy traffic of 10 gigabit per second. And then we ran 2 instances of the INT collector, one collecting data every 100 milliseconds and another collecting data every 500 milliseconds. And this is the outcome. What was supposed to be 10 plus 70, 80 gigabits per second, it only reflected a quarter of that, right? Or a little bit more than that. So it clearly showed that the solution, it had to be improved because we don't want to have this kind of gap in our monitoring. So this is the driver. This task here, this graph was the motivation to change everything. So this new solution started with 3 goals. The main goal, it was the goal number 1, is like we want to continue using INT the way it is, meaning Although it's a P4 switch, we could change the pipeline and do some of this pre-processing on the pipeline, but too complicated. Let's keep the processing this outside of the forwarding plane and our monitoring nodes. The second goal is no more static gathering interval, as I mentioned before. The third one is monitoring bandwidth utilization and storing that data when there's a pattern change, when there's bandwidth variation. When we see that if you have a flow that is constant 1 gig per second for 1 hour, does it make any difference if you monitor this every second, 5 seconds, 10 seconds, 10 minutes, or 1 hour? It doesn't, right? Because you know that it is not going to change. You know that it hasn't changed. So you don't need to save all the intermediate points of measurement. You just monitor the before and after. So this is what we want to do is to tweak the pattern. So every time we receive a counter, we process against the previous values and see if that data is useful or not. So our implementation was to monitor bandwidth utilization every n milliseconds or alpha milliseconds, maybe 10 to 20. You can go down to a little bit more than that, but 10 to 20 it's enough for now. Saving the last delta bandwidth values in an array every alpha milliseconds, then we evaluate the current bandwidth against those previously saved values and multiply by a microburst factor. So this is what I'm gonna talk a little bit more about it. Monitor bandwidth utilization using this adaptive approach. All metrics and values should be customizable and dynamic. In our implementation, consider microbursts events that are shorter than 500 milliseconds. Anything larger than 500 milliseconds is going to be captured by the goal number 2. So I don't want to scare anyone with the algorithm. I have a better one, but this is in the paper, so I have to use those slides for the NUMS presentation. So I'll keep it here for now. So this algorithm 1, this is the one that detects microbursts, right? They're looking for pattern change. So it's pretty clear here. This is the formula that we get. And we added all those variables as customizable by the operator. So you have the loop interval to collect those counters. You have the minimal bandwidth. So for example, we don't consider a microburst any change that's smaller than 14 gigabits per second. If you have, doesn't matter if you went from 0 to 13.9, we don't call it a microburst because it then start polluting too much. And also there's a lot of persona nodes in our infrastructure. So then we'll always be gonna receiving alerts and notifications because of those persona nodes. So this depends also, all of those depend on your infrastructure, right? And I'll explain why. So the growing factor, it's a very important one. How fast the data changes from one measurement to another. If it grows 2 times, 3 times, 5 times. So this factor, it depends on your topology. It depends on how much you, on average, use your bandwidth. So if you have an 100 gig interface and you're always using 30 gigabits per second of a minimum, right? There's always 30 gigs. You're not going to get a factor that is a growth by 4 because that's going to imply on 120 gigabits per second. So your factor will be 1.5. So it goes from 30 to 45, or 2 that goes from 30 to 60. So, but if you only have like 5 gigs or 10 gigs of bandwidth, then you can multiply by 5. The factor could be 5. So it goes to 25, 40 gigabits. Then you start tracking this. Then you have also the number of previous measurements. So this is a very interesting one. If there's anyone here interested in doing research, is how back should I go to compute my current bandwidth against the past, right? Should I go 2 milliseconds, 100 milliseconds, 2 seconds? So depending on that number, you get like very, very interesting results, right? Because we try to do like the 2 previous measurements, meaning 40 milliseconds. 40 milliseconds, you start detecting microbursts in the middle of a TCP data transfer that just faces 1 retransmission. So if there's 1 retransmission, the traffic it drops and grows again, boom, your application thinks that there was a microburst, because in fact there was, according to your factor. So this magic number for us now, I think is 304. And then there's microburst margin. Is like, how do you know that the microburst is over if you're not looking at the graph, right? So for the software, how does the software know? Does it have to go from 100 to 0? Does it have to go down 20% to 40%? So we did a lot of simulations, then we got that 60% was a good number. So this is the logic for us to consider pattern change. This is then we save not just the beginning of the microburst, but we also save everything that comes before. So we can see if it's growing little by little or if it's a subtle change, right? And we also save what comes after. It's not here in the algorithm, but we save the next one after the microburst is over. That's good for troubleshooting. And this is a more like simplified way of representing. If you picture this barcode, every barcode going through time and being a packet, so then you get time 0, time 1, time 2, and the variation between time is the alpha, is the interval that you predefined it. Then you have packets that are larger, like thicker than the others. You see they are aggregated together. Sometimes there is inter-packet spacing. So you can have a burst, a microburst, a big burst, and then periods of silence. It doesn't matter, right? So just represent packets. So what we do is we get this packet directly on the NIC, as I mentioned, but on the NIC, we only have counters. It's the same problem. There's no division. So we do the division on the user space. And then the user space, we collect the bandwidth 1, 2, 3, and 4, because we need at least delta values, in this case 4. So we save the last 4 values. Then after that, the 5th one, we use it and start comparing against the average of the last 4. So if this is the pattern change, if there's a pattern change between B5 and the last 4 before B5, BW5, then we save it, right? Then we save to the database. Then we wait for the next reading, which is alpha, in this case, 20 milliseconds. Then we do it again. We shift towards the right, and then we get B2, B3, B4, B5, and then we have the bandwidth 6, and then we compare against the last 4. And if we consider burst following that math, then we save it. Otherwise, we just keep going. So this is how the algorithm goes. Obviously, this is just to detect, not to decide when it ended, but I wanted to simplify here. So this is a first evaluation that we did. It was by coincidence that there was a supercomputing coming 2022. There were our friends in Brazil were doing some tests because they wanted to demonstrate something. What they had, a new link, don't remember. But then we decided to start monitoring, and suddenly, this was not intentional, we got this figure here, right? So we have this blue ellipse, which is a burst, not a microburst, it's pretty like large. So our system ignored. And then it detects 1, 2, 3, 4, 5 bursts, right? According to the figure, there's 5 bursts. And those are the parameters that we use. But once we start zooming in each one of this, then the first one, it turned out to be 9 microbursts of 20 milliseconds each. And you can see the bandwidth of each one of those. So this is the outcome of the software showing you this. And then you can see all of them, they're pretty much in the same second, 37, 37, 37, 37, 37, 37, and 38, but it's still under the same 1 second interval. And this is the zooming microburst one. You see that the first one was ignored because it's under the minimum threshold, is under 14 gigs, but everything else was reported here. You can kind of estimate here, 3730, 3730. So this is the first one. So there was also the duration. You can see here 20 milliseconds, 20 milliseconds, and there was 60 milliseconds. It's not the one in this figure, is this one here, number 3, right? Yeah, it should be. So this is the outcome, and then it gave us the possibility of having a summary, and this is how much space I'm gonna use for this whole period of what? 13 minutes, right? Instead of saving every 20 milliseconds a counter, I only saved this table. Is a summarized report. telling when there was the duration of the microburst and the maximum bandwidth that was identified. I know if the duration of the microburst was smaller than 20 milliseconds and our alpha was 20 milliseconds, this number could be a lot higher, right? If it was a microburst. But then you just adjust alpha to operate as every millisecond, for example, and eventually microsecond. I never tried a microsecond. The second component, well, questions to this point?
I haven't seen any come in yet.
Okay, so we're almost over. The adaptive monitoring here is the part that I was mentioned before, that we only want to say the data that makes a difference, right? And this motivation, this figure here in the bottom is the motivation. You can see here that we have each one of those green balls is a measurement point, right? So those dots here, that means that there was an actual data counter that was stored that was used to create this graph. But look at this interval here, this valley. Look how many measurement points we have, but this is pretty much constant. If we grab just the first one and then the last one, we could have created pretty much the same graph and save the disk space equivalent to all those intermediate dots here. So this is the part, is like we're trying to find a solution that was efficiency in terms of saved storage, like how much storage can I save, and accuracy when we compare two charts created, the original with the solution. So the logic is pretty much the same. You start getting packets, right? But the difference here is that the interval that before was static, it was the alpha was static, now is the one that it's customizable, because we decrease or increase according to the change and the pattern. So we get the first one, the bandwidth 1, we wait, and then again bandwidth 2 after some interval, and then we compare those two. If we see that there was a radical change, a radical here, we talk about 15%, then we increase or decrease. So if the bandwidth was way high, then 15%, we decrease the interval, so we want to get more data. If we see that it's slower, they're pretty much the same, then we decrease the interval, we give more space between the measurements. But you have to be very careful. Those two, like decrease and increase factor, they are key to the success of the solution. Because once you detect that there was a change, a radical change, you don't want to wait too long, because then you could miss the rest of that event. So you want to decrease interval as fast as possible. So we're evaluating the best approach to decrease this interval. And this is how we evaluated the solution. This was a work that Italo did. He compared, like he used these two algorithms for image comparison, called PSNR, the peak signal to noise ratio, and SSIM, which is structural similarity index. Those algorithms are used for video quality analysis and image comparison, picture comparison. So the PSNR, it has this scale here. If the number is greater than 37, it's excellent. 31 to 37, good. 25 to 31, acceptable. And the SSIM is 90% excellent. 75 to 89, good. 61 to 76, acceptable. So he created two sets of figures, one that report the last 30 seconds, and then one that reports the last 30 days. And he created multiple setups. Those setups were like playing with those variables that we have here in the algorithm. And those variables that he used here are all in the paper that will become available in a couple of weeks. But those are the results that he got, right? So except for this one, the PSNR was 26.48. Everything else was considered good quality, right? And the SSIM, we even had one here that was considered excellent in similarity. And then you can compare those here in this figure. So the green one is the original, is the one that had all the measurement dots. You see that we have peaks and valleys that in some cases were not reported, but this is a very small interval. Here, this figure exactly, it's 30 seconds, right? So days over a day, you wouldn't miss anything. But these ones, depending on their size, they could be detected by the microburst detection system. So they kind of complement each other. But you can see that the test 6 here and kind of went like completely off because we missed all this window here, this space here. But the red one was pretty close to the green one. So it's a good way. I didn't know those algorithms. This was great finding. It's a great way for you to evaluate if the images that you created are good, because otherwise I would have to be looking one by one. And keep in mind that everything that we do here, we do to support the network operation, right? So we want our network operators to have the best information possible. So we have to be careful when we create these graphs to make sure that the graphs report the reality. So just to conclude this version 2.0 of the INT collector, it was developed to support as many customizable variables as possible, to be dynamic, to be customizable on the fly at runtime, and to save disk space. This was not just disk space, but also CPU, right? But mostly like space. The few trials that we had demonstrated that, I forgot to talk about the efficiency column, right? So you can see that we got from 53 to 67% of efficiency, meaning that we saved that much space compared to the original graph. So the green line has 100% of the measurement points. The red one has 33% of those, right? So that means that we have a lot less points of measurement, and we use a lot less space, disk space, and we still had something pretty similar. So this is remarkable. And now, well, not now. So as a follow-up to this, part 2, the idea is to start discussing is like why and when it's important, right? We want to showcase the science drivers that we model, and to help you understand that you have to do the microburst monitoring, or maybe not. That's not your use case. If everything for you is best effort, you're great with whatever you have. But if you have SLAs, if you have real-time applications, then in some cases it's better for you to have a little bit extra visibility. And for the Vera Rubin use case, which is the use case that we all the time are focusing on, they only have a couple seconds to do the data transfers in every microsecond. We tested so far, even the smallest microsecond during the 5 seconds long haul data transfer sets off everything else. So this is what we want to show you all. And that was it. That was the goal of this talk. It's almost an hour. Sorry for that. I hope it was productive, and I'm available for questions.
Yeah, thank you for going through the entire thing, Jeronimo. Really comprehensive. So those that do have questions, you can either use your raise the hand feature, or just type in the chat room. I know that we're at the time here, but I can stay a little bit longer to sort of answer questions and help people ask questions if they would like. I have a couple. Most of mine are going to be related to the application side of this, and what you've seen when you're running it with the science applications. So I'll hold off on some of my questions until the next round. But I guess my first couple that I was interested in is, you are optimizing for sort of CPU and storage and things like that. What's a typical deployment strategy going to look like for this? Do you envision this sort of living next to a given switch, or is it going to be a centralized sort of thing? Maybe just a little bit of info about how this could be deployed.
Our goal, the way we structured the network, was that every site has a node to receive all. Well, every site has a parallel management network, just like 10 gigs and 100 gig ports, to redirect all the traffic to the collector that sits on that site. So one in Santiago, one in Sao Paulo, one in Miami, one in Atlanta. So each site has this kind of node. It's a powerful node. It's just one rack unit, but it's a 3.1 Intel Gold CPU with a very fast disks. And the idea is that these nodes, they parse everything like these million per second times scale packets, and just send updates to the centralized database, which sits in Miami. So yes, every site that is every big site has a node like this. For the sites that are too small, like for example, Panama, then we just re-inject the traffic into the network because then it becomes like a couple megabits per second. And then we bring this to Miami.
Okay. And I don't see anybody asking a question quite yet, so I'll say it again. If you do, just raise your hand or type it in. The last one that I sort of had was, since there is a lot of challenge in capturing this data, I mean, maybe just a really quick, if there was any particular use case that was more challenging for you guys to capture than others. I'm assuming that for the really fast speeds, that's going to be the hard one to capture, but did any specific hardware or protocols give you trouble when you were sort of prototyping this?
Yes. Well, the main one is receiving all those reports, even per site, because if you have a distributed traffic nature, like multiple flows and multiple sources and origins, then the next, the CPUs and the multiple cores, you can do hashing and you can do load balancing. But when you have someone doing experimentation with a 40 gig flow, right? That is the same source, same destination for everything. All those packets, they land on the same NIC skill on the same CPU. And then you might have 128 CPUs, but only one is going to be used. And then you're talking about 4 or 5 million packets per second. So if you do this, the version that we presented last year was doing this before the Linux kernel, but it was still in the main CPU. And then we managed to get to 2.5 million packets per second. But we start seeing some struggles with those when you have 4 million packets per second. So what we decided to do was we had to refactor the whole code of flow to the Jeronimo card, which is a programmable card that supports eBPF and P4. It's like now costs $1,500. Used to cost $600 before the pandemic. Now it's $1,500. So you can push that code to the NIC. And then now we managed to get 14 million packets per second with no drops. But now you have a much less flexible code, right? Everything has to be fully customized. There's no division. There's a lot. There's no pointers. There's no recursion. There's no threads. So the code becomes very specialized for the hardware, but the scalability now is impressive. So we can get to the point that we're only going to use one collector for the whole network. You need to have more than 800 gigs of traffic generating reports for this NIC not to be capable of processing.
All right. Well, thank you again for going over all this in detail. And we said that the next one is going to be June 2nd, I believe.
Yes.
Okay. Well, those of you that are on, the next one will be June 2nd. That's also the next time that we'll have any talk, because we don't have another one scheduled for a little bit. So hopefully we will see you all then. And I'll make sure that I get the slides and the video for this posted. So I hope everybody has a good weekend. We'll talk to you all soon.
Thank you all. Thank you, Jason. See you soon.